With a review of sort of known and conjectured results for, let's say, Anderson-type binding model in one and more dimensions. So let me just remind you of my notation again, since it's been a while since I spoke. And we will look on the lattice. We're going to be on a lattice ZD. And our Hamiltonian will be the discrete Laplacian, which I defined last time, plus lambda, which is just some parameter, positive, times a potential V, which depends upon the lattice site. And it has a, remember, V are independently distributed, and they have a common distribution, G of V, which is between 0 and some bounded by some constant. You can think of Gaussian cases. You can think of something which is uniformly distributed between -1 and 1. One thing you can't think about, or you can think about, but it's a hard question, and I won't cover here for the most part, is when the case, this only takes discrete values, plus or minus 1s, for example. And those are Bernoulli. They're quite interesting, but they're, the results in this area are sort of sparse, and so I may make some comments about that later. So let me let P of AB be a projection onto this, a spectral projection of H on the interval, spectral interval AB. And then I'm going to talk about time evolution right now. I'm going to come back to time evolution and tell you some things about that. Again, review some things here. And so remember, so I take an initial condition psi 0, and I solve the, so let me see, let me write it like this. If I let psi of t equal e to the minus I t h psi 0, and I'll assume that psi 0 is supported near 0. So we can think of it as compactly supported, but sometimes I might want to assume a little bit more about it. It doesn't have to be exactly compactly supported, but sometimes I may want to assume that the projection for a particular interval AB, I might want to assume that it lies in that spectral projection. So occasionally I'll want to assume that this is equal to psi 0. So that means that that psi 0 is really made of eigenstates that live with energies that live in that interval. So this is, but for the most part, you can think of this as just being a delta function that lives at the origin. And so just to review a little bit from last time and to continue, we defined r squared of t to be the sum of psi of t x, and then I take the absolute value squared and I multiply by x squared and sum over the x in my lattice. So that means this is the mean square. It has the meaning of mean square displacement of a particle which is initially has a wave packet supported near the origin, and then it may spread. So this this may grow, and it's a very intuitive notion of how the wave packet spreads. When later on I will consider higher powers of this. So so you might want to consider r to the 2m. And then I would put a 2m on here, and I would ask how that spreads, how x to the 4th or x to the 6th spreads. But for right now, it's I think we'll just keep it at 2, and then we'll come back to that later. So, so first fact is that for any such potential on the lattice, we have the following result. R squared of t is always less than some constant times t squared. And that is a fact. This constant is really independent of the v that appears here, and this follows from the famous Duhamel formula. Maybe I'll come back and say a little bit more about that later. Since I did improve it last time, I might get a chance to do that today. So this is for all v, for all potentials. There's no, I don't have to take any expectation. By the way, with this g of v, I will, on this board, let me just indicate that I will often let this script e be the average over the v's. So that's another piece of notation which I want to say something about. Okay, b. The other fact is that I mentioned last time that if lambda is equal to 0, okay, so I have just the Laplacian, or I might have the Laplacian plus the periodic potential, then we know that, in fact, r squared of t goes like some constant times t squared. So it does spread linearly. It does spread. X spreads what we call ballistically. So this is sometimes called ballistic motion. Okay. And now at the other extreme, so these are both fairly trivial statements. And the next one is not so difficult either, in hindsight, certainly. And so this is C. We're on ZD. Just to emphasize again that these are and lambda. Suppose if lambda is much larger than 1. Okay, so this is now sort of the opposite case of what I've been talking about here. Then we have the following statement, that now I have to take this expectation, the expectation of r squared of t is less than some constant with no time. So it doesn't spread. No spreading of the wave packet. And this is sometimes called, I'm not sure of all the fancy nomenclature that's around, but this might be called dynamical, because it's time, localization. Okay, so this is a theorem which is goes back to many people are involved. I won't go into all the names, but this is generally well understood on the lattice. This doesn't give you a complete picture of what happens. First of all, it is special to the lattice. If I were in R3, such a result would certainly be false. Okay, you would have to project your eigenstate into a low energy state, and then you would have a chance of its being true. But that's why I need these projections here, because sometimes I want to restrict my size to lie in some zone of energy. The trouble is with this result in high dimensions, if I just take a delta function or a function of compact support, it may have some eigenstates that live at fairly high energy, and then all this lattice picture is really not very accurate anymore. And you, at high energy, you will presumably have extended states, and so you will not see this behavior. So this is really a very much of a lattice statement, unless in the continuum you would have to put in some projection. I would have to assume that psi 0 was equal to E psi 0, where EAB, and A and B would have to be some fixed interval, let's say, near the origin, or low energies. So you would have to pick a zone where it had, So this function here can't have compact support, but it will decay very rapidly. You can arrange for such a thing to happen and have it decay very rapidly. Yes?
By E, you mean P?
Oh, yes, I do. Thank you. I do indeed. Okay, so that is the. So this is the theorem. I mean, these are sort of so this is a theorem on dynamical localization, and we'll see many versions of this later on, which are more energy specific, but I just thought I would contrast it with what we have here. And so are there any questions about what I've got so far? I'm going to tell you some more about dynamics, so let me just stop and ask whether these statements are clear. And I encourage questions, comments, so please, if you have any questions? Yes?
Shouldn't the strip is smaller than constant to be localization? Because if it is equal to constant, it's...
No, less than or equal to a constant. I mean, I don't know how it depends upon time, right? I could sort of fluctuate around like that. This just means that the wave packet, this just really means that the wave packet doesn't really spread much, right? There's no, in other words, if I look...
Constant is diffusion.
Hmm?
If it is constant, then it is...
No. I will, so there's no T here. This is maybe I should say, maybe that my C. Yes.
So how do you average on potential?
I beg your pardon?
What's the potential average?
This is, you see, so these are good questions. So R squared is defined as I have above. You see the psi there. Now the psi evolves via this Hamiltonian. So the psi has randomness in it. So I need to average this thing. Okay? This is not true without averaging, because if I didn't average, I might be so unlucky as to take a v which is constant, or a v which was periodic, or something, or quasi-periodic, or something like that, or just zero, right? So this is not a statement that's true without averaging. You have to average. And so it's a typical statement. It's true. You could also say this is true with probability 1. That would also be an equal, essentially equivalent statement. But you need some kind of statement that this is, you need some kind of averaging. Yes,
Well, if it is for almost all realization, the constant will depend on omega?
If you have, but the expectation will not, because it's expectation.
No,
but if I say, yes, if I say for almost all, then I need to say r squared of t is less than some constant, and that constant's finite with probability 1, but it could depend upon the potential. That's worth saying. That's worth saying. So that's why I wrote the average. I didn't have to say it that way. Victor.
Not constant.
Yes.
Is it uniform?
Yes, it is. Yes.
Yeah.
It's uniform.
In distributions of V and in lambda.
That is correct. Yes. Okay. Any other comments about this? Yes.
Just fix psi naught and then take the average of the R squared, or you just claim that.
I pick a size 0. Let's say, just think of a delta function at the origin, and then I try to see how the wave packet spreads, and so this is really telling me, in some sense, it may have some weak tails, but they're summable, right? It doesn't really spread in any sense at all. And in fact, I could put, if I wanted to maybe emphasize something, I could put an m here and an m that appears up here, and then I could put an m like that, and I would still have a constant. The constant might depend upon m, but I would still have a uniform bound. Okay. And this is sort of the intuitive notion of localization. This, of course, implies pure point spectrum for everywhere. All the eigenstates are now localized, at least if I let my psi be supported in a general way. This really implies, so this is a strong statement. It really implies pure point spectrum. Again, with probability 1. Because we all know that if you're not careful about how you choose your potential, and if your potential is not random, you're not going to see the effects. So that's.
You're telling us. You're not expecting us to. Immediately
I'm only telling you this, right? So the only thing that I said last time that might help you understand why such a thing is true is last time. Remember, I considered a couple of extreme cases. In one extreme case, I made lambda be very large, and then I dropped this. And in that case, it's obviously true. You can't spread at all. You just sort of oscillate around the support of your of size 0, and you can't spread. Right? So this is really a perturbation, if you like, off of the diagonal case. In a crude way, that's really what's happening.
No, I meant inferring the pure point.
No, that's
found. You're not
no, that's a general fact in mathematics, but I don't expect everybody to know it. Sometimes it's called a Rage theorem, Ruel, and so forth. But no, I'm just going to state it. Today I will prove very little, but I will just try to give you some overview. Yes.
Can you explain the meaning of the interval AB in
Yes.
many dimensions?
Yes. So why do I take this? Well, for the experts here, you see, if you want to do the continuum, you really have to make sure that your initial state lies in some narrow range of energies. If I don't do that, it could have some components in the absolutely continuous spectrum. In general, if I have a continuum Laplacian, I will have point spectrum at the lower end, but I should have extended states. And in order to make a statement like this true in the continuum, I need to put it in this projection. And I need this projection to lie in some low energy region. And then if I make my coupling constant large enough, and that will depend upon A and B, then I'll see the same phenomena. So remember when I was explaining the reason for looking at this rather than the continuum, the idea was that these guys had the same, same physics, but only at low energies, not at high energies. Okay? After all, this is discrete and momenta is bounded here. So the notion of high energy it doesn't even make sense here. So, but at low energies, and that's why you can then use these projections, you can make pretty much the same statements in the continuum. Okay, so let me move on. If you have more questions, let me say something. I'll say something more. Now, in d equals 1, of course, we've been hearing from Ilya and Leonid, and we know, and it is a proven fact that if lambda is not equal to 0, not just you don't have to make lambda large, then again we have this expectation of r. Let's say 2m t less than some constant times well, the constant might depend upon m. In fact, it probably does. Okay, so that's a statement of localization. It's dynamical localization in one dimension, and you need to have this this lambda not equal to 0, because we know that if lambda is equal to 0, you're going to spread ballistically. So this is a very abrupt transition, and I think when mathematicians first hear about such a thing, they think this can't be. I'm adding a very, very tiny perturbation to my Laplacian, and I'm getting completely different dynamics. This is bounded by a constant. The other one for lambda equals 0 is bounded by t squared. So that's quite a change. Now, okay, so let me make some other comments, some general remarks, which I think are important to keep in mind in this thing. So I've said a lot about the continuum and how you have to be careful with projections, but now let me make some comments about the fact that it's very important that v of x is time independent. Of course, I've assumed that, and everybody else who's spoken here has assumed such a thing. But in many cases, especially in nonlinear cases, you might want to be considering time-dependent systems. The time dependence might be periodic, it might be quasi-periodic, or it might be random. So let me make a remark, which I think somehow is not so well known in the mathematics community, but it actually is an important remark, it seems to me. So suppose I have v of x, and I now add a time dependence, and I'm going to assume that the v's are basically on the lattice. I'm going to be on the lattice because it's always the simplest. So the v's are independent for different x's, and I will assume that the v's are independent in t. Now I have to be precise about that. What I mean is, if I take different times, so separated by some unit length, then at different times, this potential looks different. It's independent of what it was before. So there's independence in x and in t. Okay, and now this actually makes the problem much easier to analyze. Surprisingly, perhaps it isn't so surprising when you realize that really this gives rise. Your system doesn't have any memory. One of the important things about localization is memory. This potential will change. You wait long enough, you don't like the potential, it'll change. And so if it were to come back to where it was before, it will see a completely different environment, and it will see it's like seeing a new environment every time it moves. And this is basically some kind of super Markov process. So you don't have to understand all that, but I will try to explain it a little bit. And so let me state the theorem. There is a theorem. And it says that if I look at the Schrödinger equation, okay, so here I have the time dependence. Then you do not get localization. You do not get ballistic motion. You get diffusion. And that doesn't really matter what dimension you're in. So in dimension 1, 2, 3, those are the dimensions we're mostly going to be concerned with. There's a theorem of Cherymchantsev which says that r squared of t averaged, I define it exactly the same way, grows like some constant. I'll call it d because it's like a diffusion constant times t. Okay. So this is a different behavior. Yes. You have to be very careful in the continuum. Okay. So this is discrete. So I should say this is for ZD. So this is a good question, because in the continuum, you can get quite different behavior if you're driving the system. And the reason is, after all, when you have a potential which is moving around, you are actually potentially pumping energy into your electron. And actually, there are certainly cases in which you can get ballistic or even superballistic behavior. Okay? So you have to be extremely careful. And that's because, now why can't that happen on the lattice? Well, your momentum is bounded, okay? But in the continuum, you run the danger that your momentum might undergo a random walk. And that's very bad, okay? So that will change all this picture. So you have to be careful with that. So it's very important that this be ZD. And there are actually quite interesting questions. To my knowledge, not really proved, but there was some controversy in the literature in the continuum. And I think a plasma physicist, very famous one, Marshall Rosenbluth, studied this question and got all kinds of exotic behavior depending upon how the times were correlated, how rough it was in time, whether it was delta function correlated, smoothly correlated, and you can get all kinds of exotic behavior. So it's important to keep that in mind. Any comments or questions about that? Yes?
Are you surprised that, like, the case that you just put very small lambda, you get another behavior, you just put a very small time dependent?
That's right. That shows you these things are sensitive. and well, you see, I mean, this is in a way not so surprising because you really have some kind of a Markov process. You can close the equations up very easily. You can't do that with a fixed configuration. So I think this is a very interesting line for people to think about, because so here I'm assuming that these are sort of rapidly decorrelated in time. But if you allowed yourself longer and longer time decorrelations, then it would
This
be
is
very,
certainly when t goes to infinity.
yes, this is large T, large T.
This is what
And as lambda goes to 0, d as defined by this equation will grow and diverge.
Absolutely. Yeah. Yes. Yes, that's right. So, so this is so how d depends upon lambda, how d depends upon the I mean, you know, you can interpolate if you wanted to. You can interpolate between a time-dependent potential and make the time correlations longer and longer and longer until, in fact, you know, you're essentially studying the time-independent case, and then your d will certainly then reflect dimension, and you will see many of the properties that we've been discussing here. So it's a nice problem in which you can interpolate, but of course, the longer the correlation time is, then the harder it is to do the analysis. If it's short, it's fairly easy.
Sorry.
Yeah.
It's a bit hard for me because t has dimensions. So large means what?
Well, I'm on a lattice, so I don't have to worry. It just means that I have a bound. Actually, I have an upper and lower bound of this type. And in his theorem, by the way, there's a logarithm here. It just means that if I wait long enough, it doesn't matter what the time is. So you're asking the dimensions. I mean, this is the dimensions are all contained in the diffusion constant.
That should be connected to lambda or.
It is. I mean, you know, I'm assuming. I'm sorry. I didn't say that here, but I'm very much assuming that lambda is not equal to 0. Okay. And in fact, this is what I wrote. I didn't have any lambda, right? So. Okay. All right. So, okay, let's continue. So this is a little bit more of the philosophy.
But what about high dimensions? Why?
Still fine.
The
As
same.
far as I know, yes, still the same. Still the same. So another little comment. Since time dependence is actually a fairly important notion, suppose I take a potential. I'm digressing a little bit, but I don't think there's any harm. I take a potential well. And we all know if the potential well is deep enough, or I'm in 1 or 2 dimensions, this is a well which is negative, I will form a bound state. Okay? And that means that my particle will forever live in such a well, and that's the end of the story. However, suppose I make this well time dependent, maybe even time periodic. Time periodic is a little bit more subtle, but okay. And then I study the corresponding equation. Now this is a single well, single bump, and I have time dependence, and I make the time dependence periodic. I keep the well so that every time maybe it just moves a little bit up and down like this. Just does a little bit of that periodically. Then I would say this is a generic statement. It's not. You have to be somewhat careful about the statement, but the roughly speaking, generically, and I have to say a little bit about it. If you start with a wave packet that lives in here, it'll all go out to infinity. None of it will be left. You'll have no residue of the bound state. Okay, so the wave packet radiates away, and that shows you it's part of the same picture. It tells you that if you have a well, even if your well for any fixed time will always have a bound state, the time dependence will destroy, typically destroy. And this can be done. This can be understood through Fermi golden rule, or I'm just stating these as results right now, and maybe piquing your interest about why such things are true. And in fact, it's not trivial to prove these things are true. And there are special, very, very special cases where they're false. And these have to do with integrable systems and breathers and this kind of thing. But in a generic sense, it's true. Yes.
Is this true in the time average sense, like 1 over t integral of radius? Is how you see
how it radiates away?
Yeah.
It really does radiate away. In other words, you look at the you pick a wave function, integrate over some bounded region. goes to
Goes to
0.
zero.
Yeah, it does go to 0.
Could you state please the conditions of this? Because if I just move it very, very rapid, so nothing happens.
No? Well, on the lattice, I should say, when I say this, this is a continuum picture. On the lattice, you're right, because I can avoid this problem. But let me make this statement in the continuum. And in fact, one of your colleagues, I think, Avi Sofer, has worked on statements very much like this.
If your time periodicity is very, very slow, follow the eigenstate.
Yeah. You can try to follow it, but there'll be a radiating piece. Eventually, there'll be a radiating piece. Yeah. It's not a trivial fact. But you see. Yeah, so this is just a warning about how time dependence can really influence.
Like the adiabatic theorem, if we go slower and slower.
It'll be longer and longer, but it'll take a longer time to get out. Yeah.
Why
Yes.
is this behavior destroyed in the lattice?
The lattice, you can choose high enough frequencies so that it doesn't see it. You can give examples of such things.
Question again, I describe why. Because if you connect that large D, and what large means with that constant in A or constant in C there, then that's very nice spec, because you can study the dynamics of your state and get the localization lengths, or I don't know, something related to localization phenomena. Is there a relation? Is there a rigorous relation?
Well, there, as I was sort of alluding to, if you make your time correlations longer and longer, so that your potential is constant for a very, very long time, and then only slowly switches over, there will be a crossover between localization and this phenomenon. Yes, and that D will change.
But in that theorem, is that a relation between the largeness of that T with that C in your?
Which C?
The C there. There are two constants there.
This.
Yeah. Which.
Yeah. That'll blow up too. That can blow up too. This C could be huge. I didn't say anything about how big this is. I mean, it isn't huge in this case, but.
Is it like that large T equals that large C, or that 2 times that C? Algebraic relation?
Well, they're related by the crossover time.
Yeah.
So in a situation that you envisage, the diffusive law will hold for short times up to some characteristic timescale Tc, and then beyond that you will switch over. I mean, if you sort of go to this the time-independent case where localization should hold, you cross over to this, and so to go one formula from one formula to the other, you need to know this characteristic time.
Yeah.
Back to my question.
Well, I'm not telling you how it depends upon a characteristic time.
Okay.
I'm not telling. I did say this is sort of time independent, which means at short times I haven't decorrelated. That's the assumption. If you make those times larger, that D is not uniform. That's maybe your comment. But let me move on here, because otherwise I want to go back to the time independent domain, since that's the purpose of this. But I think it's important to keep all these pictures in perspective. So now I want to tell you about a theorem which somehow interpolates between some of these things. So this is the theorem of Cherem-Chantsev that I mentioned, and actually he has logs, upper and lower bounds of logs, but there's some recent work by Jeff Schenker, that I think gives this on the nose. So what about 2 and 3D? And lambda small, because we already discussed lambda large. So let's make lambda small now. Now this is the difficult region in general. Okay? And the theorem I'm going to state is not very exciting, but it's important to know, so I will state it. And it's actually, in the strength I'm going to state it, it's fairly recent, believe it or not. This tells you that the expectation of this guy is, roughly speaking, I should say, some constant times t squared. Okay, that's ballistic motion, but your t can't be too big, so the t, let's say, t should be bigger than 1, and let's say less than lambda to the minus 2. Okay. So in other words, if you think about, so this is a small time scale, a relatively small time. It's a large time scale compared to if lambda is small, but it's still not very large, right? So it's telling you that a particle in one of these random potentials really behaves ballistically. Okay? This is ballistic behavior for quite a while. Okay? But then it will cross over and start to behave diffusively. But this is the ballistic time scale, and lambda to the minus 2 is considered to be, roughly speaking, your mean free path. In other words, the typical distance that the particle will go before it gets scattered. Okay? So that has to do with this time, and x and t are essentially comparable here. So so when you think about this sort of at an intuitive level, you say to yourself, well, I have a particle moving along here, and it's in a weak potential, so it'll pretty much go in a straight line. It might have a little bit of funny business, but then at another time scale, it starts to get scattered and scattered, but this length here, at which basically little happens, is lambda to the minus 2. Okay, and you see this length in one dimension, actually, also. This is the localization length, roughly speaking. Okay, and it's basically ballistic until it hits that length, and then it says, "Oops, I have to come back. I can't go any farther." But I'm going to talk about 2 and 3D. So this is a relatively recent result, which is, actually versions of it go back to Herbert Sloan many years ago, but I think with this it was sharp constants this way. Relatively recent work of Thomas Chen based on some work of Yao, which I'll now explain. So let me say what the main conjecture is.
Question, yeah.
Yes, sorry, I missed.
Don't you have the same result in lambda?
Yeah, basically you do. Mm-hmm.
Okay, so it's
Yeah, it's pretty general. Mm-hmm. You do. You do.
So can you please lift the board so that one can see it there?
I'm sorry. This? All right. So now let me go to the main conjecture and some partial results in this direction. Take one of these erasers here. So the main conjecture, I think I can erase this. So you understand this ballistic and localized time scale, and then we also saw this other time scale in which you, if you have time dependence, you see diffusion. Well, the main theorem of or the big conjecture, let me say, from a mathematician's point of view, this is something that I should say historically is obvious to physicists, but mathematically it's quite non-trivial, and it remains open after many years of effort. So here's the main conjecture. I would formulate it like this: main conjecture, and this is on Z3. Z2 is a little different, as we discussed last time, but let me say what should happen, and that is that the expectation of r squared of t should be d, another d from the one that Cheremitchov gets, of course. This will times t. Okay. That it grows diffusively. This is diffusion. And this is the time scale here. Lambda to the minus 2, t. Yeah. Time scale has to be bigger than lambda to the minus 2 to see it. Otherwise, you see this behavior. And then if you just think about what this means, it tells you your diffusion constant here is of order 1 over lambda squared.
And this is for lambda small.
This is, yes, thank you very much, David. This is lambda for lambda small. And this was lambda small, but it's good to put it down every time. Mostly I'll be discussing lambda small, because lambda large we kind of understand at this point. I mean, at least I mentioned what the results are. I don't claim I've explained why it's true, but so this is the big conjecture, and it tells you that the particle, it's sort of obvious from a physical point of view if you see this little path I've tried to draw here, it sort of goes in some direction classically, and then it turns because it gets scattered. It turns some more and turns some more. And these turns, if you can imagine them to be independent, that's a big question, you will see diffusion. If I imagine a particle being buffeted about by some fixed array of scatterers in space, you would certainly expect it to be diffusive. Of course, that's not correct in 2 dimensions. There actually is localization. And these problems, by the way, classically, you can ask these questions classically. They're just as hard, classically, in my opinion, as they are quantum mechanically, and possibly harder. And I'll say a little bit about that. I mean, in quantum mechanics, you're doing linear theory, really. In classical dynamics, of a particle in a random potential, you're doing nonlinear theory, and you want to understand the long-time behavior of this particle. So,
Can you resolve the classical results? Say
yeah, I will
fixed
explain it
scattering.
just a moment.
Stationary? This conjecture is for the stationary.
Yeah, it's this case over here. These are IID, all with a common
Those
distribution.
theorems for
Yes, I stopped the time dependence. Sorry. I have finished with my time dependence story. That's worthwhile clarifying. I beg your pardon. So this result here and this result here are for the time. I'm finished with time dependence. Okay, so I'm now in the time independent regime again. All right. So now, so what do we know? So you may think that this is not an interesting result, and certainly one could hope to do better, but it is the best result by far that we have in mathematics, and so I should, being a mathematician, I feel I need to state it. And this is the theorem of, since it's fairly recent, only within the last few years, of Erdős, Salmhofer, and Yau. I believe it's in the Acta Mathematica. And what it says is that this condition, very simply, star holds in the following time regime. They don't quite state it this way, but it's essentially equivalent. Okay, that's a hard theorem. So I see, in fact, I'm being generous with the 0.1.
2.1 could be 2.01.
It could be 2.01. That's probably more like what they say. I'm being generous. They should have a 3 up there, by the way. I mean, but they have to. That's too hard. I mean, they have to do. This is done by intense. This is probably the hardest, rigorous result, these days in the subject, and in fact, how is it done? It's done by perturbation theory. They do it at the resolvent level. No, maybe they do it in the time dependent. It doesn't matter how they do it, but it's done by perturbation theory, and lambda is a small perturbation. And to do this properly, and I'll explain a little bit more about it maybe next time, you have to go to order n, where n is very large, where n is like lambda to the minus alpha, some alpha positive. Okay. So as lambda gets small, you have to compute more and more diagrams, and you have to set up a little machinery so that you can control this. This alpha is like the 0.1 probably that appears here, or some variant of it, and then you can say something about it. And basically, it's this result and this one here are of course related because they can cover both regimes, but they concentrate on this. So what this means, if I could just say before I ask for questions, this means that they are somewhat into the diffusive regime, right? They do see diffusion for a certain time scale, a certain non-trivial time scale. And as I say, this is hard work, and one hopes that this isn't the right way to do it for all time, because if it were, we'd never get there. And in fact, there are obstructions to doing this beyond 4. The methods are simply impossible to go beyond 4. And you expect it to be true for all time scales. So it just can't be done by this method. But this, I have to say, this is what we know. And so it is a remarkable result. And it may lead to some further insights into this problem of diffusion. But that's the best we have. So there was a question, sorry. Yeah.
I wanted to clarify that this is rigorous and that's conjecture, because
Main conjecture up here for all time scales, no bound on t, and this is the theorem. This is an octa.
It's done by very high orders of perturbation.
Exactly.
Counting Feynman graphs and bounding them individually
Yep.
and trying to do the best that you can.
Yep.
You don't get very much.
You don't get very far.
But still parametrically further than lambda.
Much. I mean, it's a big step to go from lambda squared to lambda to the minus 2.1. I mean, mathematically, they have a right to be proud of this result, although it is such a small step compared to what we'd like to understand, right? It really is sort of sorry that way.
Sorry.
Yeah, sorry.
So the early dynamics are ballistic.
Yes?
And then at 1 over lambda squared.
Yeah, about that time. It's not sharp. There's a constant. I've been sloppy with constants. So at order lambda squared, it would depend upon energy and so forth. If I project, it would depend upon size 0, and so it will. But this is meant to be impressionistic. But roughly speaking, lambda to the minus 2 is correct.
But there is a point at which there's a sharp change to diffusive motion.
Well, you see, they do. I've set it up, if you'll notice, so that they do match. Right? If you look at lambda squared, I've set up the d so they actually do match. But one shouldn't take that intermediate zone too seriously. I mean, they're about the same. Right? It's hard to really distinguish. But it is this kind of picture which you should have in mind, that the particle basically goes straight, but then there's some time scale at which it will, I mean, it's not a sharp time scale, but it will start to turn. And these turns, if you imagine, they might be very slight turns, but then eventually, if you keep on making slight independent turns, you can imagine that classically, anyhow, this particle would be.
I guess what I'm asking, I mean, is it natural to think that perhaps you can just put an exponent on t and that exponent changes smoothly rather than you have this?
No, I think this is a better picture. I think this is the more accurate picture. In other words, I think it pretty much goes ballistically for that time scale in a range. Okay, so I should say this square should be a little bit fuzzed out, perhaps. Right? But it's around there. Okay. Yes.
You promised to mention some classical results.
Yes, classical result. Classical result's very nice. So after this paper of Erdős and Salmhofer and Yao, there is a paper by Komorowski. And he does the classical version. So what is the classical version? And his methods are somewhat different. In fact, I think it's actually very, I confess I haven't read the paper except for the statement of the result. So what would we, and this is in the continuum. And by the way, the work of Salmhofer and Yao is in the continuum. So that's a small point. So you can just think of it on the lattice. But it is actually in the continuum because it makes the computation of the diagram simpler. You just have p squared and you don't have this cosine stuff running around. So that's a technical point. Now really to do this classically, what is the statement? So the statement is something like this. I have a potential. I have p squared plus lambda v. That's my Hamiltonian. And I will assume my v is, let's say, bounded but fluctuating in space. And then I look at the Hamiltonian equations of motion. So roughly speaking, I will have x double dot of t equals, let's see, minus lambda gradient of v of x of t. I just write down the Hamilton equations. I've just written them down here in vector form. So I have a particle subjected to this force, and I have a lambda that sits in front of it. This omega, this v is random. So I just like this one, except that you should think of it as being smooth and independent in different pieces of space, then you have the same behavior classically. In other words, there'll be a time at which x squared basically moves like this. Then this is the picture, right? So the main result is that for t, the motion, typical motion, same thing. Okay, it's a classical picture like I was trying to explain here. And I think this is a barrier for him too. I think maybe he can do a little bit better in terms of this exponent, but I think there's also a barrier for him to go beyond that time scale. And what is the problem? The problem is memory, okay? The problem, as I was trying to explain, if the potential were, this potential were time, were changed in time, this would be a Markovian type process, and you could set up an equation for it, and you would see diffusion. But this particle will come back typically, or at least occasionally, to where it was before, and this causes troubles because there's not an independent step anymore. You've got memory of where you were before, and this is really the origin of localization in some ways, and certainly in weak localization and so forth. You have to worry about such problems, and the fact that they're non-Markovian is a major source of problems, and it's a common problem in both classical and quantum dynamics. And I would say in some ways the quantum dynamics has a chance of being somewhat simpler. They're both difficult, but has a chance of being somewhat simpler because at least you've got a linear set of equations. These are highly nonlinear equations, right? They're not this v, of course, is a non-trivial function, and this is a nonlinear equation. Yes.
Sorry, I didn't get that. So, what is the problem about the self-process?
Okay, I didn't explain that very well. The problem is that as the particle moves through the medium, okay, it can come back to where it was. If it always sampled a new medium, if it always never returned, for example, to where it was, it would essentially be sampling something new every time. It would essentially be a Markov process. But what keeps it from being Markovian is the fact that it can come back, okay? And that comes back to my point that I made at my first lecture, that Brownian motion doesn't like to come back to where it was very often in 3 dimensions, whereas it definitely does in 1 dimension, right? And in 2 dimensions as well. And that's really the origin of that's why these things are not so independent, okay? It's this recurrence problem.
But Tom, I'm a little puzzled. I mean, I
Yes.
appreciate that both problems are difficult technically.
Yes.
And
comparable.
it's because it's non-Markovian.
That's right.
Somehow
That's right. That's correct.
Physics-wise, it seems to me that quantum mechanics is very different from classical.
I'm not saying they're the same.
Quantum theory,
They're not the same.
We have the wave interference,
Right.
And we know it is destructive.
That's right.
Usually, and,
Yes.
and that's what's going to bring about localization whenever.
Yes, but it requires if you have time dependence, right, then you won't have that interference, right? Yeah. So it's a very similar. I'm just saying they're analogous problems, and they're not. Yeah. Go
Just a
ahead.
related question, but if I remember correctly, maybe not, that in Lorentz gas,
Yes.
we could prove, although it's classical motion, static obstacles,
Right.
Not random, but in a sense.
Yeah. If you take a periodic Lorentz gas, this is a very famous problem with finite horizon, what's called finite horizon, then in fact it is an example of what Martin and you were maybe alluding to. Quantum mechanically, you should see, I would expect to see actually ballistic motion, but classically you see diffusive motion. Okay. Classically, you definitely see diffusive motion. However, if you make those scatterers jiggle them around a little bit, then I would expect to see diffusive motion in both cases.
Is the D in the classical and in the quantum calculation the same?
Well, they're probably not so far apart. Okay. I mean, I've defined this in the continuum. I wouldn't say that. No, I would be a bit more cautious. I don't know the calculations, the classical calculations well enough. The classical calculations are quite tricky, and in some cases you will see. I mean, numerically, people see some some slight logarithmic superdiffusive behavior, which is not so typical of the systems that I'm talking about. So they're not exactly the same, of course, as Martin is right to point out. And of course, there's quantum effects are also very important. But there are enough analogies so that if one really understood one, I think one would learn something from. I think they're instructive to understand both aspects of this problem. Okay, so I'm not moving along very fast here. How much time do I have? Well, okay. Yeah. Yes, please.
I'm from different department.
Yes.
From Department of Physics here.
Yes.
And these two problems are well known, of course.
Yes.
In physics as well, and they are both, as you said quite correctly, logarithmic in two dimensions. The difference is that sign of interaction, of mode coupling, is different. It is interference is destructive in quantum problem and constructive in classical.
Okay, I'll have to figure out what that means, but maybe you can tell me afterwards. Okay, so now let me go back to, let me talk about, now I'm finished talking about time dependences, and I've talked about a little bit of classical time dependence, a little bit of quantum time dependence. Maybe I should say one other thing that fits together, sort of jumping around in my talk, but I guess it kind of fits some of the things we're talking about. So let me do the following. So now I'm also going to say, this is another thing. This is actually a theorem, and I will come back to it because I think it's important enough to explain. It does not have a classical analog, to the best of my knowledge. So remember let's look at one dimension. I'll say Z1 first, and I will make the following assumption. Assume R2M of T. Remember, this means, let me just very quickly, psi of X, psi of J, of T squared, and then I will have an X here, X to the 2M. Well, let's suppose this is what I'm going to call subballistic. Okay, assume it's subballistic. What that means is that if it were ballistic, I would have a T to the 2M here with some constant, which might depend upon M. It certainly would depend upon. That would be ballistic behavior. And what I'll do to say it's subballistic is I will put in here a gamma, and I will assume that gamma is strictly less than 1. Okay?
Yeah, I still get that thing about particle remembering its memory. When you take the average over all the paths, that should disappear. Why don't you say that the...
Well, it doesn't really disappear. I mean, the fact that it doesn't disappear. That's the short answer. You can ask me afterwards. Otherwise, I won't get to what I want to say here. And I'm sure there'll be plenty of questions about this too. So let me make some comments about this. So now I want to assume that this is true, and then that M is large somehow. Okay, and M might be large depending upon this gamma. Now, if gamma is very close to 1, I might have to make M very large. If gamma is not so close to 1, I probably don't have to make M so huge. But this is a sort of a quantitative statement. This is just times gamma here. So this is just a quantitative statement of how fast your wave packet spreads, and the theorem, which I would like to state, is that you cannot have this behavior. If you have subballistic behavior, then you're localized. Okay? In one dimension, you can either be ballistic. Okay, this is for random Schrodinger. Okay, I don't want to say it for any other context. then the statement is this implies gamma less than 1 implies localization. Okay. There's no intermediate time scales. Okay. No intermediate time scales. And this is 1D. Okay.
Just to understand the statement.
Yes.
So you assume that
Yeah,
this is a
assume.
behavior, and then you
Then,
prove that
yeah.
localization in which sense? That actually it's constant.
Absolutely.
That
Actually, it's
gamma
fine.
is
All right.
zero.
Yeah.
Expectation.
In expectation. Sorry.
Ilya Goldscheid sense there's just one Lyapunov exponent. It's either 0 or positive. That's
okay,
it.
okay.
No more to the story.
Yes. But this also applies for strips. Okay. Any strip still works. Okay. And if you assume something about this gamma and the C.
Tom, if the strip is wide enough, you will have an intermediate diffusive regime. You have to be more careful as to there's possibilities to scale and.
But I'm looking for very, very long time.
Long time.
Long time. When I write this, always long time. Okay.
We've been discussing intermediate time.
Okay. So this is for long time. Thank you for clarifying that. Okay. Eventually, it localizes. Certainly, there's an intermediate time scale. All these problems typically have some kind of intermediate time scale.
But it can be parametrically large.
This constant can be quite big. I'm just saying it is bounded. It doesn't grow. And that implies point. So that means that if you have any kind of, and this is basically, this really basically goes back to the ideas of Thouless. And Thouless, this is a version, a sort of rigorous version of Thouless scaling. So let me say what happens in 2D. In 2D, the statement is the following. If gamma is less than 1/2, that means strictly subdiffusive. Then that implies square root of t. Okay, so you don't have these intermediate time scales cannot happen in random systems. So these are not hard theorems to prove. In fact, one of my students, Wei-Min Wang, worked this out. I think actually had been worked out. Certainly the ideas behind this go very much back to Thouless. See, Thouless always assumes that you have some kind of diffusion in your system, and then he wants to say, well, if I assume diffusion, which is the usual picture, as we heard from Phil Anderson, that in the old days they always assumed everything diffused, and then you find out, well, really, that if they did diffuse in one dimension, and you take it in a strong sense, this is a strong sense because I got these m's running around here, and m can be quite large, then you will in fact learn that it has to be localized. Okay? So
an assumption on the potential in this theorem is independent of...
Absolutely. This is always a standing assumption. Always a standing assumption. Okay? So the G of, so I have a potential. It's just the assumptions I've been talking about all the way through. Okay? I'm not making any comments about other scenarios. I mean, I'm sure you could, but I don't want to go there. So I will try to explain why this is true, maybe, hopefully next time, but I don't know whether I'll get to it. Right now I'm just trying to paint the picture. And there's a similar theorem in 3D, and you can imagine that if gamma is less than 1/3, the same thing holds. So you can't have, if things grow too slowly, then they get trapped, roughly speaking. They got to escape somehow, right, in order to survive. So that's the 2D statement. Now let me go back to this diagram, and I want to say a few words about this diagram and some problems. Okay. So I drew this diagram, and I'm going to draw it again for you and make some comments, which I think maybe I wasn't so clear last time, and I'm sure there'll be many more questions this time about the diagram. So I'm going to go back to I'm in 3 dimensions, and I will consider general lambda, but I'm always considering this tight binding model, so I have a discrete Laplacian and so forth. And I want to try to explain this picture which I drew last time, which is a fairly interesting and I think important picture to have some understanding of, certainly. So this is my energy axis, and this is my coupling constant axis. I wrote this picture for you last time. I will make a few more comments about it because let me assume that the V's, this is helpful. Let me assume that the V's lie between 1 and -1, and they're sort of uniformly distributed there. Then for lambda equals, so this is going to be my lambda axis, so lambda is the coefficient of the Laplacian here. It's just some positive number. And I will assume that the V is symmetric, that has a symmetric distribution, so G of V, G minus V, they're all the same. And then we have the following picture that we discussed last time. At lambda equals 0, the spectrum runs from 0 to 4D, 4 times the dimension of the lattice. The spectrum is a compact set there, and of course we all know that the spectrum at lambda equals 0 is absolutely continuous, and in this region you have, as is well known, you have ballistic behavior. But once you turn this lambda on, all kinds of things happen, but the spectrum is very simple to describe. So the spectrum itself, there's a line that basically comes out linearly because of the way I have this thing set up. You can see that the spectrum will occupy this whole this whole region here, inside here. There's no spectrum out here. No spectrum. No spectrum sitting out here. And then we would like to be able to say something about where the localized states lie and where the absolutely continuous spectrum should lie, because I'm in 3D. And so the part of this, as I said last time, will be conjectural, and part of it will be theorem. So I won't draw this curve, of course, yes.
Say again, what is E?
Sorry?
Could you say again what E is?
Oh, E. E is the energy. E. Oh, 4 dimension.
Oh, okay. 3.
If I'm in 3, that would be 12, I guess, right? 4. Yeah, 12. Okay. So because your Laplacian, if you compute the spectrum of the Laplacian, it will run from 0. Well, in 1 dimension, it will run from 0 to 4 because you have 2 times cosine. So let me just do that little calculation for you so it doesn't look too strange. In 1 dimension, remember, in Fourier modes, it's 2 times 1 minus cosine p. Now, p can go from 0 and all the way up to, make this thing change. So p equals 0 would be 0, right? And then I can change, if I choose this to be pi, do I want to choose it to be pi? Yeah, I think I want it to be pi. Then I get a 2 here, so that goes up to 4. So 4 times 1. Okay? And if you have several of them, you just add them up and you get 4D. Okay? So my spectrum here, we know everything about it, everything about the eigenstates here. And now we want to turn the lambda on and see what happens. And this is what I was trying to describe last time, that you will get a curve, and if you look at the numerics, it's pretty much like this. And I will assume that the distribution, that G is even, so this is pretty much mirror images of each other through the axis. And as I mentioned last time, this is all repetition more or less, except I want to be a little bit more careful about what I said. So in this region, now I should be still, the shaded region, we have localization. And this is fairly precise, especially if lambda is small. So this guy comes in sort of quadratically tangent to this line. And then in this little region around here, you know that you have localized states. Yes?
Can in principle absolutely continuous and pure point spectrum spectra overlap? Or is it?
No, they don't. You can have, at a particular energy, you should only have point spectrum or absolutely continuous. But there's a little bit of a crossover, which I have to describe, and that's one of the things I wanted to do with this picture. Describe what happens along this boundary. Okay, this is a very interesting area. But inside here, we should have extended states. But I have to stay away from the edges of this, away from the edges here, right? Because you have a crossover that comes here.
Some simple argument to explain why you cannot have both spectra at one point outside.
Why you mean simultaneously have point spectrum and absolutely continuous spectrum in the same narrow interval?
No, they are support on disjoint sets.
They are on disjoint sets.
Disjoint Borel sets. This is the last Yakshit theorem.
Thank you. Okay, so yes, it's I actually didn't know the theorem, but it's something I should know. So so now let me make a few statements here just to clarify some things. One very important measure of how things look for the eigenstates is to look at this inverse participation ratio. So I just want to make a few comments about that and about what happens in here. So this, if I look at in the finite volume, I should see, as I mentioned last time, a GOE, Gaussian orthogonal ensemble statistics, because I don't have any, everything is real in sight. I'm on a lattice, but that makes no difference. And in 3 dimensions, if I'm in a zone, an energy zone, and I have a large, very large volume, and I look at the eigenvalues and their spacings, the conjecture is, this is conjectural, this is, the shaded part is proved, the conjecture is that I should see GOE statistics.
Large but finite, because otherwise...
Large but finite volume.
But you can take the limit.
Yeah, you can take a limit.
And scale.
And scale.
Finite,
Right.
finite scale.
Yeah.
You must take your volume large enough, and you must make sure that your energy interval doesn't get too close to this boundary. So that's what I didn't say very carefully last time, because it's very interesting to understand what happens near this boundary. Not very well understood mathematically or even, at the level of physics, but at the level of numerics, it's extremely interesting and it's an extremely challenging problem. So localization in the shaded region, roughly speaking. And so I want to explain a little bit of this. I did say something about it in shaded region. So I wanted to say something more about this. In this region around here, this is an area which I've spent a little bit of time thinking about, but in a way, it's almost a trivial area in this region that you get localized states. So I want to make this point. In this region, for small lambda, and I'm not in here, the density of states in this region is exponentially small. So the statement, to be more precise, if the energy is less than minus lambda squared, the expectation of V0 squared, times the Laplacian inverse on diagonal. I can do this, and remember, I can take the mass to 0 in 3 dimensions. That's the fact that random walk is transient. And then I maybe need to subtract something O of lambda cubed, something of this kind. Suppose my energy is basically over here. Then the density of states, so this is this is done by perturbation theory, is exponentially small. So it's really ridiculously small. It's something like this. It's, you don't really have eigenstates down there. You do have them. I mean, there is spectrum down there. There are eigenstates down there, but they're extremely rare. Okay? And so everybody knows about Lifshitz tails. That you know that the density of states is very small within this little neighborhood here. What I'm telling you is, I'm telling you how far you can go in, to some extent, and still see Lifshitz tails. And that's the statement of this. And this easily implies, as I tried to explain last time, this gives you localization. Okay. In 3D. Now, this in 2D you can't quite do this. In 3D, I mean 1D you have to. There's some other power that appears here, but there's always this region. There's a region which you can understand quite well, where the density of states is really ridiculously small, and that means that the wells are very, very far spread apart, and so forth. Okay. So now there's something else I wanted to say here. So what about at the, so in here, if I pick an eigenstate in here, and I look at psi, let's say alpha x raised to the 4th power, then this will go like 1 over the volume if I'm in a big volume, some constant. And I should take an expectation, and I sum over x. And I'm assuming my eigenvalue here, psi sub alpha, has energy in this range. Okay? So that means that the wave packet is really spread all over the space uniformly. Okay? So these are all question marks. Now, if I picked my eigenstate over here, then this is not going to be true anymore, almost surely. And one sees numerically multifractal structure, which means that depending upon the power here, I will get different powers on the volume that I have here. Now, if I went to the, let's say, if I went to the 6th power, I would have, there's a simple scaling. You're just saying that the eigenstate is maximally spread out. But at the boundary, at this mobility edge, there are all kinds of very interesting things that happen, and you may hear about some of that from Ludwig's lecture. I just thought I would mention it. Now, what can we do mathematically in this region? Well, as I said, I mentioned this work of Yao, and I'll mention some other work of Yao, since he's very active and interested in this area. But just to show you what the problems are. Was there a question? Okay, thought I heard somebody asking a question. Anyhow, let me now really simplify this problem. And you think, well, we surely would know the answer here, and we do not. We know something, but we don't know what we'd like to know. So this is very recent work. Some of it's been published, and at least some of it's in preprint form, of Erdős. This is Benjamin Schlein and Yao, H.T. Yao. Okay. So this concerns n by n matrices, which, you think everything was known about n by n matrices. So we'll let H be n by n symmetric matrix with real entries, IID, subject to being symmetric. So this is, a very important thing that I will assume is that the HIJs, independent, not Gaussian. Otherwise, what I'm going to say is very well known.
So you're completely changing the model.
I'm completely changing the model.
Because you can say nothing about the one.
That's right. So the one I described up here is the one we'd like to solve, right? So what I'm going to do is I'm going to take a mean field model, the closest mean field model I can think of, and something that everybody here seems to be quite interested in from discussions I've had. They want to understand how, Jan's been discussing it in his lectures. We want to understand how a matrix, a symmetric matrix with random entries, how its spectrum looks. Does it have GOE? What do the eigenfunctions look like? So this is the question I'm addressing here. And I made a lot of publicity for this, and I guess somebody was listening because they went and solved the problem, but it's not a trivial solution, and one would hope for better solutions again. But so what can they prove? So these are independent, not Gaussian. It's very important that this is real. These are real matrices. Okay. So we would expect, of course, as we know, we would expect GOE. Just like I said up there. Right? We don't know. We don't know this. I mean, it's an embarrassment, but it's just a fact.
In what quantity?
In the eigenvalue spacing distribution. Okay.
Or even in pairwise correlation.
Yes, pairwise correlation. So energy-energy correlations. You should see the same law that you do for the Gaussian case. I mean, there shouldn't really be anything very different. You might worry about what happens at edges, but I'm talking about what happens in the bulk. At edges, actually, we do know that this has Tracy-Whittem behavior, but I'm talking about inside the bulk, and there we don't know. Okay. So what else would we like to know? So we don't know this. Now, I mentioned up here that that it was conjectured that the participation ratio was behaved like this. This inverse participation ratio had this behavior. So let's see what that means. In the context of this random n by n matrix, we pick a wave function psi, and I'll assume that E lies somewhere not at the edges, because edges have funny behaviors, and you might get something different, and they don't allow for that. But then the theorem says that psi, the eigenstate psi of J, because this is indexed by J that goes from 1 to n. This is an n by n matrix. I'll use the letter J to denote the fact that. Now notice I have no spatial structure here at all. I mean, every matrix element has the same distribution. And we can talk about more complicated cases, but this is already tough enough. So we'll assume that this has norm 1, as I always do, but I'll just emphasize it here. And then what they prove, so this is J goes from 1 to n. So what they prove, and I put this a little higher up here, is the sum of psi j to the fourth, j equals 1 to n, goes like 1 upon n, which is exactly what you'd like, except they're missing a little bit of a log. But it's not too bad. I forget the power here. I'll put in a 4. It might be actually 8. But anyhow, this is the main.
No, they prove that there is log there, or they just cannot.
No, sorry.
It's not. Yes. Okay. I'm really.
There's no log there. There's surely no log there.
I hope.
There's no log, but they can't prove it. Okay. So that's the statement. They almost get the extended state, but they don't quite.
Well, you have to be somewhere near the Gaussian. If you go very far from the Gaussian
yes.
distribution, you certainly do not.
You mean Cauchy?
What do you think? So make a comment about that, please.
Well, you see, if the distribution stops having moments.
Oh no, I'm sorry.
With high probability.
Yes, no, that.
Matrix will be 0.
No. I will assume that all my distribution has all nice moments. Every moment is finite. So let's make it compactly supported. Okay. So let me put that in. The Hij's are, let's say, bounded. Well, the distribution G of V. How do I say? Yeah, it has compact support.
How do they do? They just maybe few. What is the methodology?
It's very special to this case. In fact, I went through the paper quite carefully. It's quite tricky. It doesn't. I tried to extend the methods to band cases and couldn't do it. It's perturbation theory again, but it's a little bit.
Perturbation in what?
Well, it isn't actually perturbation. It is not really perturbation theory. They could have done it with perturbation theory, I think, but no. 1 upon n could be a parameter. You can do.
One over n.
Yeah,
Okay.
you could do. They don't do it that way. No, I don't think I have a nice clean answer for that question. I should have, because I read the paper in some detail a while ago, but I can't remember precisely how they did it. The idea is to use these finite rank perturbations, and
They do not appeal to, say, resolvents or green functions.
not really.
Not really.
Not really.
Okay.
I mean, I sort of expected them to because of the earlier work, but they didn't do that. Okay. So now, yes. Let me see here. I did that. Oops, I'm almost out of time. Let me just finish up with one other question. I mean, I would like to do something else, but obviously I'm running out of time. So I will now explain a question which is, you know, for us mathematics. Yes.
Do you need any averaging there?
I do. This is with high probability or with an average.
Okay. But for which j? What does it mean j? How you select j? J is not random variable.
You pick the j is the index. So psi is an eigenstate. You pick an eigenstate with energy.
How to select this eigenvalue?
Okay. You pick any one you like. You take a soup of all these things, and it's still.
Probability. You have to give some definition.
Yeah.
What does it mean?
So I believe that I can say the following thing, that if I take psi alpha j, the fourth, then for every energy, for every alpha, which is an index corresponding to energy inside the bulk.
Alpha eigenvalue is converged to a certain random number in the support of the density of. This is more or less one.
Yeah, I have to assume that the e's don't go to the edges. So now let me make I have 2 minutes left, and now I will tell you a problem which is not really, it shows you where some of the mathematics is moving, and it's not an area which I believe is so interesting from a physics point of view, but I thought I would at least, since the problem is so simple to state, and there are such illustrious mathematicians working on it, I would at least state the conjecture and state the result that they have. So this is a problem. I don't know how old it is, but I think it's actually quite old. You have an n by n symmetric matrix. With entries which just take values plus or minus 1. They're independent entries plus or minus 1. Okay. So I have a matrix, and I'll call this as a random matrix M. Okay. Then the question, there are some partial results due to Terry Tao, one of the recent Fields Medal winners, and his colleague Van Wu. They've been working on this quite hard. But just to show you, now Terry is considered, and rightly so, the powerhouse of analysis within mathematics. And here's the question he asked and has been working on. What is the probability that the determinant of M equals 0? Okay. So, I mean, you know, this is a discrete set. It can't be 0. If it were continuous, you could say it was 0, but it's not. So what do you expect? You expect, and even he will tell you you expect this, you expect that it's exp of minus some constant times n. In other words, you think about 2 rows in your matrix, and you ask what's the probability that they're proportional. And you'll see that's pretty rare. Okay? What can he prove? Something like this. Okay. 1 upon root n, or 1 upon
It's
n.
much more probable.
So this is a bound.
What mathematicians can prove.
This is what you expect, and this is what you can. This is not so good. So I don't feel so bad. This is what the point of this little exercise is to say I don't feel quite so bad that I can't solve these other problems when he can't solve this. That's the talk for today.
Let's thank Tom. We're breaking for lunch, and at 2 o'clock, Zoom with the lecture. We're starting a new lecture series. This will be Andreas Ludwig.